In this example, we will solve the initial value problem, y double prime plus y prime minus 12y equals 0, with the initial conditions that y of 0 is 2 and y prime at 0 is 1. We could do this using the methods we learned for solving second-order differential equations with constant coefficients, but here we'll do it using the method of Laplace transforms. Now, taking the Laplace transform of both sides, we get that the Laplace transform of y double prime plus y prime minus 12y is the Laplace transform of 0, which is just 0. Splitting up the left-hand side using linearity gives us the Laplace transform of y double prime plus the Laplace transform of y prime minus 12 times the Laplace transform of y. But we know that the Laplace transform of y double prime is s squared times the Laplace transform of y minus s times y at 0, which is 2 here, minus y prime at 0, which is 1. And the Laplace transform of y prime is s times the Laplace transform of y minus 2. Cleaning this equation up a bit, on the left-hand side we have s squared times the Laplace transform of y minus s times 2 minus 1 plus s times the Laplace transform of y minus 2 minus 12 times the Laplace transform of y, all equal to 0. Now, to solve for the Laplace transform of y, we collect all terms involving Laplace of y on one side. We'll move these to the left and everything else to the right. This will give us s squared times the Laplace transform of y plus s times the Laplace transform of y minus 12 times the Laplace transform of y. Factoring that, we have s squared plus s minus 12 times the Laplace transform of y on the left. And this is equal to 2s plus 3 once we add s times 2, 1, and 2 to both sides. It's worth noting here that s squared plus s minus 12 is the same as the characteristic equation that we would get if we solved this differential equation using our previous methods. The last step in finding the Laplace transform of y is to divide by s squared plus s minus 12 on both sides, giving us that the Laplace transform of y is 2s plus 3 over s squared plus s minus 12. Now that we know the Laplace transform of y, we need to find its inverse to know y itself. So we need to find the Laplace inverse of our above Laplace of y, 2s plus 3 over s squared plus s minus 12. In our first order example, we used that the Laplace inverse of 1 over s minus some constant a is e to the at. But here we can't directly use that because our denominator is not linear. It's s squared plus s minus 12. So to find the inverse here, we're going to need to factor our denominator. S squared plus s minus 12 factors as s minus 3 times s plus 4. So we can rewrite the Laplace transform of y as 2s plus 3 over s minus 3 times s plus 4. Now we can use partial fractions to split up the Laplace transform of y. By clicking on the pink link, you can see that process of partial fractions done out. Doing this process and finding the partial fractions, we get that 2s plus 3 over s minus 3 times s plus 4 can be rewritten as 9/7 over s minus 3 plus 5/7 over s plus 4. Writing it this way, we can compute y as the Laplace inverse of 9/7 over s minus 3 plus 5/7 over s plus 4. The Laplace inverse of 9/7 over s minus 3 is 9/7 times e to the 3t, and the Laplace inverse of 5/7 over s plus 4 is 5/7 times e to the negative 4t. In both of these terms, we are using that the Laplace inverse of 1 over s minus a is e to the at. As noted before, in this example, just like in all of our examples for Laplace inverse, we follow the same overarching process. First, we took the Laplace transform of both sides. Then, we solved for the Laplace transform of y. And finally, once we knew the Laplace transform of y, we needed to find the inverse in order to find y itself. Here, and in many examples, we needed to use partial fractions in order to find that inverse.